Hi, everybody. Thanks for being here. It's good to have a nice presentation about PIANC MarCom, the Maritime Commission, which we're going to have. We have around 350 people who have agreed to join. So it's my pleasure to welcome you and kick off this meeting. So that's what I'm going to do. My name is Egbert van der Wal. I'm the chair of the Maritime Committee within PIANC. I'm also the father of two wonderful boys, and I'm the director of port development for the Port of Rotterdam. The program for today is an introduction by myself about what PIANC does, but also what the Maritime Committee does, who we are and what we are, what's at stake. A presentation of automation of container terminals by Asjeber Jacob, presentation of the vendor design by Alfred Raubels, and at the end a presentation of what happened to the Ever Given in Suez Canal, the incident by Everett Laterre. So first, what PIANC stands for is it's the global organization providing guidance for sustainable waterborne transport infrastructure for ports and waterways. Just putting this into this picture because I also know that there are plenty of people in this webinar who are not at the moment PIANC member, and I think it would be a really good idea to join. It's a forum wherein professionals around the world join forces on our on the expertise we are working on, and it's the longest standing organization within this field. If you look at the mission of PIANC, that's to remain the leading international source of waterborne transport infrastructure related information within the 21st century. That's not because we want to be relevant, but because we see that there's still a need for expert guidance and technical advice to ensure that everything that's being engineered, being constructed, and being used is all that we need it to be to ensure that our ports stay healthy and people can do business. To keep the international waterborne transport community connected, there are a couple of conferences and congresses. The nicest one, I think, is the 4-yearly PIANC World Conference, which is going to be held, the next one in South Africa. The date is not yet finalized, but probably in a year. The other two are the International Conference on Coast and Port Engineering in Developing Countries and the Smart Rivers Conference, which is more about inland waterway transport. And we also support young professionals and countries in transition. I think the young professionals are the future of our game. We need to embrace them into the expertise which we want to share. If you then look into the Maritime Committee, then the Maritime Committee is, I think it's what says in this picture is what MarCom is all about. It's about the design of terminals, it's about port planning, it's about land reclamation, it's about erosion control, sustainability, but also smart infrastructure, life cycle management, approach channels. It's all that is necessary to run a port, but also to design and to build a port. And that's also something that we are working on from the Maritime Committee itself, but also with the members of MarCom. We have around 55 members of 25 countries across the globe. What I feel most proud of is that the level of expertise, not only within the Maritime Committee itself, but also within the working groups is phenomenal. There are people working on the tunnels in Norway, on huge reclamation projects and everything which is in between. MarCom cooperates a lot with other international organizations like IMO, the International Association for Ports and Harbors, but the newest one is the OSIMF, in which we share our knowledge, but also they give input in our new guidelines. And I think that strengthens the cooperation but also ensures that everything that we make is fit for purpose. If I then look a little bit back into the latest reports which we have been made, then it's about renewables and energy efficiency for maritime ports, the design principles for dry bulk marine terminals in 2019, ports on greenfield sites, berthing velocities, which Alfred is going to talk about, and the planning for automation of container terminals, which Shibber is going to talk about. We have 23 active working groups at the moment. Some which will be finalized shortly are the recommendations for the design and assessment of oil, gas, and marine terminals, design for terminals for ro-ro and ro-packs, the mooring of large ships at quay walls, and the recommendation for the design and assessment of marine single-point moorings. And I'm very proud that they're almost finished. If you then look at the upcoming, the latest ones which are started, then we started a new one for the planning of fishing ports, a nice addition to the, let's say, to the terminals in which we look at fishing ports and how they evolve in the latest decennia. The second one is the seismic design guidelines for port structures. There are guidelines, but we see that with new insights in seismic design, but also in predicting infrastructure, it's imperative that we make a new report for this. Then the mooring bullets and hooks selection, maintenance, and testing. It's the most important thing to hook a ship to the quay wall to ensure that mooring is safe and sound. And there is still a lot to be done at the moment, and we are proud that we are starting this one. Mid-ocean related risks during construction of marine works. Another one in everybody knows that if you work close to sea, but also with marine and infrastructure projects which take a long time, it's imperative that you come up to risks, especially related to mid-ocean risks, which can endanger your construction of marine works. We're looking into how to cope with those, what the basic risks are, and what we can do to ensure that everything goes safe and sound. Inspection of maintenance and repair of waterfront facilities. We see a lot of aging infrastructure within our port in Rotterdam, but in many other ports. And inspection, maintenance, and repair, doing that as efficient as possible, ensuring that everything is up to the specs to be used safely. I think that's a big challenge, and we are very happy that we have a really nice group of people working on the new report. The ship dimensions table 2021, we put a date next to it, or a year, because we see that this is something that will be evolving during time. We use a lot of ship dimensions in our different reports, but it would be we thought it was a really good idea to ensure that we have one central document in which we can refer to, in which we can add once it's necessary. The guidelines for the use of BIM, building information modeling in infrastructure for ports and waterways, also something which is somewhat new, but also already existing. There are a lot of international guidelines available, but how to use that and what the gain is by using BIM in your projects, that's something that we just kicked off now. And I have very high hopes of this really nice report. Mitigation of tsunami disasters in ports, also a topic which is still evolving, and we are trying to see if we can enhance our guidelines to give expert advice. The one I'm very proud of, also because it's one of the working groups which was being done by our late colleague of Australia, is the guidance for ports in small island countries. And this is the first guideline which we are not making only by ourselves, but we are including the World Bank and also including the Asian Pacific Investment Fund on infrastructure. A really good opportunity to ensure that also the smaller parts, small islands, can use our information. Then the last thing that I want to say before we kick off the rest is that we have two new topics coming on. So if you're interested in sharing your information, sharing your knowledge, it's always good to have a little bit of an idea what's coming up. And the two things at the moment we are planning from the Maritime Commission is that a guideline for the planning and implementation of shore power connections. There's a lot at the moment already existing in different forms, but we still see that it's a struggle to get the right kind of project and get it done swiftly. And the second one is safety by design and execution. I think if you build like PIANC does, a lot of best practices on how to design a terminal, how to execute projects, you also have to have an opinion on how to look to safety by design, what the role is of a client, a consultant, and a contractor, and how at the end of the day you can ensure that everybody who is working on your projects and at the end using the infrastructure can go safely and soundly back to their loved ones at the end of the day. So that was my main presentation. Thanks for that. And I would like to introduce Ashibar Jacobs as the next speaker. Thanks very much.
Good morning, good afternoon, good evening, and thank you, PIANC, for allowing me to share my team's Group 208 planning for automation for container terminals. I'm here representing a large group that I will describe shortly. What is happening in the port or container terminal industry? I mean, they've been trying continuously from the inception to optimize all the processes, to find what they do better in the future. This has been happening for a long time, especially as the waterfront land becomes less and less available. Consolidation, densification requires a lot of processes, which is just similar to industrial systems. So that's what automation is. And then with that, as you can see with our iPhones, technology has improved significantly. Equipments and computers, terminal operating systems significantly improved. So these two aligned and made it cost available for the operators or ports to have a cost-effective way of implementing automation. But we always have to understand the initial cost of automation is high. But there is some benefit, sometimes significant benefits: improved productivity, lower labor cost, operating cost, and lower operating cost and greater degree of safety and reliability. So planning for automation also became a natural process in transition towards the sustainable and resilient supply chain. I don't have to say a lot about supply chain. Every newspaper you read today about ports is optimizing supply chain. As you know, the container terminals are a dot or a point in the supply chain system. The next stage that we will see is optimizing the whole system and making it work as one instead of a silo. The guideline focuses on planning process of automated container terminals. In our team, we had 25 active, dedicated, smart, and experienced members from 8 countries. But it didn't stop there. We had support from the industry as well. Here are the names first for the working group 208. Please, when you see them, thank them. They didn't get a penny to do this. They are highly experienced, busy people, but they were dedicated in providing or sharing information based on their experience. But not only the core team, but we did get an input from industry experts. Our goal was, if we publish this, it has to be acceptable, and then we have to be able to get a feedback if we're not doing it right from the industry, be it from the equipment side, automation, control systems, or TOS, terminal operating systems, terminal operators, and thank you for their contribution. We're comfortable that this is a good document. And the reason I say they were really dedicated, it all happened during COVID shutdown. And we had a few meetings before COVID, but mostly was virtual. And imagine many different time zones. People were willing to get up at 2 a.m. in the morning, or staying up until 11 in the evening to attend these meetings, workshops, and were able to achieve this document quickly. So back to the document itself. The document defines the planning process in this 6 or 7 major pieces. The first one is the business case. Don't start planning until you define your business case. So that is what tells you you've achieved a different level. Otherwise, if the business case is continuously changing, it has to be documented, and all the core team players have to understand it and know what they are implementing. So define it early, and then start the planning, continue to do the engineering, implementation, and operation. It goes even after operation, continuous improvement. But the key word here is integration. It starts from the beginning to the end, an integrated way. You cannot do this in a silo. All the work has to be integrated from a planning all the way to operation and continuous improvement. So when we talk about automation, starting from the water side, we have the key cranes, the horizontal transports, and the stacking cranes. So I'll talk a little bit more in detail about each piece, but these are the pieces: receive and deliver to the water, receive and deliver to the gate and rail, and manage the stack and transport it from one system to another. But there are many other technologies that make it happen, be it GPSs, in many ground transponders. All this have to be there. Some of them are buried, some of them are in antennas, but all working together are what make an automation terminal function. So it's not only about the equipment, it is about the whole system working together. Some proven concept, there is a manual operation. Many of you in the port industry are familiar with this. Some still use containers on chassis. Others use RTGs, rubber tire gantries, or front-end loaders, or combination of both. Struts and CRMGs, these are typical manual systems that we've seen. The difference between semi-automated and fully automated is based on the horizontal transport. In semi-automated, you use manned or man-operated horizontal transport system. In fully automated, you use automated AGVs or auto shuttles. Definitely Autostrad is another machine that does transport and at the same time used as a stocking equipment. But Autostrad, Strad is available both in auto and manned. There is some companies are working hard to automate RTGs. But we haven't seen it yet in a full service. So maybe someone will correct me later. So always start with business case. Business case starts with why are you building it? Where is the market? Where is the volume coming? And how is it happening from day 0 to day year 20, 30, or 40, depending on what the design life is. Then we go into the technology, preferred technology, and how is it, what are we expecting in terms of productivity? What are we expecting in terms of transshipment, or is it, what percentage is it? Is it 90% transshipment, or it is 50-50? All those have to be documented in a system so that it allows us to develop a system that works. And most importantly, based on those, we have to know what is our budget in terms of capital cost, and then what are we expecting in terms of OPEX or operational cost. Develop a financial model that can track the return on our investment. This is just a living document, but it has to always be updated and have a buy-in by owners, senior managers, and the core team that are implementing the system. But it's not only that, but there are other drivers in the business case. We may be doing it because it is required to meet some environmental requirements, zero emission and others, social impacts, safety, and always assess your risk and come up with a mitigation ahead of development. But sometimes just automated terminals are developed for prestige or for competition purposes and others. Those need to be defined as a business case for that specific terminal. So the first thing that we do in terminal planning is form a core team. This is really critical. At minimum, the core team should include, in part, a project director or manager that is responsible for all aspects of it. A member of operations, a member of equipment, a member of infrastructure engineering team, finance, TOS, IT, cyber security. All those are part of that core team, including labor relations manager, because in many areas you have to comply with the labor rules, and then you have to understand as well the legal requirements, the regulations, and having all those people working from beginning to the end assures the success of the project. So in planning, we look at, we define, as I said again, a business case. We look at opportunities and constraints. We look at the business, we develop a business process model. Potential operating modes, we look at different modes. Is it side-loaded? Is it end-loaded? Depending on different things. Is it end-loaded parallel? Is it a double cantilever? All of them have a purpose because of the shape of the terminal or mix of the transshipment. All gives you a way of solving those problems and meeting your business case. So none of this equipment are off the shelf. So simply STS used to be a 100-foot gauge. You give them the outreach and backreach and ZPMs you will deliver. None of that is real anymore. It is really highly technologically advanced and fit for that terminal's business case. The performance specification has to be developed. Is it a single trolley? Is it a double trolley? Is it tandem or quad 20s? All those have to be defined. And what is the span? And what is the outreach? What is the height? Depending on the vessel design and transfer to horizontal transport. So it is not off the shelf. Please understand that. Yard cranes, there are many yard cranes that are available. As I stated it earlier, we have the ASC end loaded. We have them parallel to the wharf and perpendicular to the wharf, side loaded. All those are been used and proven. And we have horizontal transports that can interface with STS and ASCs. And we need to look at their reliability and performance, and we have to develop a maneuvering space after selecting the equipment. So that's why it is called integrated planning. As you can see here, based on the decision of what equipment we use, we have to develop appropriate space. And we assure this appropriate space by modeling it, by creating a simulation model and making sure in reality or a digital twin of the whole system, making sure that we will achieve if we build it. Because it is a really high cost. We have to assure ourselves what we build will give us what we defined in our business case. Then even in the stacking area, the ASCs, we have to understand where it's going to be stacked, how can be maintained safely. If we have two cranes, do we have a safe maintenance area so that we can serve both ends using one crane? All those need to be defined, drawn, and identified before we finally decide to buy the equipment and finalize the design. So this is really important, and this is why we say it is an integrated planning all the way to delivery. So once we finish the planning, we look at other details. How can we do this? And then the most important is that we have to use the simulation tool, a digital twin of your facility, your sandbox that you can play with, and make sure it works. That is the closest to, if it is done right, that is the closest to building it. You don't want to build it and find all the problems. Therefore, you use a digital system to do that. And then you can use emulation to make sure all the systems, the technologies are integrated. You fool the systems by building it and thinking it is communicating with real terminal facility and optimizing your tools, your control systems, all those. And this digital twin emulation will stay there, and you can continue to use it as a training tool and others. So invest in it early on. Phasing plans. And then you're not going to implement this in one shot. There are phases. And then if it is a brownfield, it even becomes more complex and complicated. So understand those, mitigate those ahead of time. And then look at your financial plan. How is this going to make sense? And you make sure that there is no surprises. The people who are writing the check are aware of all the processes and the change, and what you said in your business case is being implemented. Finally, document this in phases of design, both for the infrastructure and equipment and operation. Once this blueprint exists, then you can give it to the people who would do the detailed design. Integration, as I said it over and over, because it is the most important aspect of terminal development, automated terminal development. If it's not done right, this is why some terminals take years to get to their business case, and some of them do not, because a lot of the integration has been done in the field and fine-tuned. You have to think about this at the planning stage and refine it before you start realizing. So as you can see, there are so many systems that have to work together. You have removed the human brain, and some computers are taking over it running the terminal. And then these systems have to talk to each other precisely for all things to be done safely and efficiently. So think about it early on. Then it goes into a detailed design. Detailed design, you have to design it. Again, importance of integration. If your equipment needs a flat ground to store containers, a flat crane rails, then you have to build it. The civil engineering has to accommodate operation, not operation trying to accommodate civil engineering. So you have to be able to drain it and still keep it flat. And then you have to use appropriate type of a pavement in different areas, because where you have a full automation, horizontal transport, getting there to do repair, you are disrupting the operation significantly. So have a durable pavement system that requires almost zero maintenance. So, but there are, this is just an example, but look at everything in a way that it will allow to operate the system efficiently without disruption. So we have to understand the construction of this are completely different. We're not going to wait for the whole terminal to be fully constructed to bring equipment. It is really integrated, where we have to to construct certain portion of the key to receive the STS cranes, commission them, test them, and use that key to deliver certain blocks of the ASCs and test them, integrate them, and go all the way to mini terminal testing, and then kept on growing, adding more and more systems, blocks to it. So that itself requires thinking at planning stage all the way to construction and to realization. So even in procurement, we have to think about all this, because what we specify for equipment or infrastructure has to be fully integrated to what we specify on both. And then when we want them delivered, all those procurement documents have to be very integrated. And finally, there are many ways of delivering these contracts. Multi-contract procurement, that's typical. But within that multi, there are certain things that we can combine. But there is this thing called turnkey, and some vendors try to promise this. My experience is this is bad. We are not there yet. And many of the problems that come in some of the new terminal developments is believing the vendors, since they are owned by one, they can deliver. And then that's not correct. And I'm sure many will come and disagree with me, but this is something that we need to discuss more. So then we have to, how do we hand over to operation? First, please understand after we go live, there is some time for ramp up. Do not forget that in your business case. The length of ramp up is, it depends on how much planning we've done, how much testing we've done, what we've done previously helps us here to go from go live into a full business case productivity for the terminal. But always remember, it's not robots running this. There are people who have to run it. Always remember to train them early on. Use the commissioning phase, the testing phase to train your labor pool. And so always start to understand the business continuity. Think about the worst scenario and how you will mitigate that ahead of time. And then definitely safety, and especially when you're dealing with technology, the cybersecurity becomes important. And safety and security are key pieces, and have experts in your team to look at those. Because one casualty, one problem will shut down your terminal. But not only that, you want it to move safely. You need to protect your human resources. So make sure that you go through independent reviewers looking at your safety system, especially where there is man and mission interfaces. And with cyber security, I think most of you know. But all this was done by this people here, and I think this is a picture at the PIANC headquarters, and I thank them for working hard, and none of this could have been done without them. Thank you.
Hello, good morning, good afternoon, and good evening to everyone. It's an honor to join you here, and I'd like to thank Ashabir for very informative and interesting presentation. We already have 6 questions that I'll be very happy to discuss during the panel, because we're running a bit behind regarding time schedule. And so I'd like to introduce our next speaker, who is Dr. Alfred Roberts of the Port of Rotterdam and Technical University of Delft. And he's going to have another interesting talk regarding the latest developments regarding PIANC applications 145 and 211 concerning varying velocities and design of fenders. So please, we look forward to hearing about your presentation now.
Yeah, thank you, Babek. My name is Alfred Roberts. I'm currently Secretary of PIANC Working Group 211, and I was also a member of PIANC Working Group 145. and my talk will be about burning velocities and fender design. Since all of you might not be familiar with fender systems, I added this picture to the presentation. So this rubber unit is called a cylindrical fender, and its main function is absorbing the kinetic burning energy of the vessel by deflection, and it protects the vessel as well as the marine structure, or in other words, the burning facility. The existing PIANC guideline for design of fender system is widely accepted in the industry. It's one of the most used PIANC documents today. However, we found out that the burning curves included in the document are developed during the 70s. So here you see the velocity curves. On this axis, you see the burning velocity, and here you see the deadweight tonnage of the vessel. So this is basically the vessel size. And you can also see that the velocity decreases with increasing vessel size. So, and also it's influenced by the navigation conditions. So this line A represents very sheltered conditions, such as in Port of Rotterdam, where this is more exposed conditions subject to big waves and currents. And Professor Ueda from Japan already showed that about 85% of the uncertainty in the burning velocity largely influences the uncertainty in the kinetic energy, also because the velocity is squared. So this is one of the most important design variables in fender design. And that's is the reason why PIANC 145 was tasked to collect data on burning velocity, because we have a lack of data of about 45 years. Ships like the Ever Given are not included in the data set which was used during the 70s. So we collected a great deal of data, more than 2,000 burning records from all over the world. 14 different ports in 7 different countries provided us with data. And our working group mainly focused on the data of the larger seagoing vessels. Personally, I looked mainly into the data of the northwest part of Europe, the data of Rotterdam, Wilhelmshaven, and Bremerhaven. You see a picture of the port of Rotterdam. And we sent out a student within the port, and he had 2 mobile lasers, and he was basically shooting at the parallel body length of the vessel. And during the stormy season in 2011, we collected 300 measurements of the big container vessels in the port. And but that was the most easiest part of the analysis. We were also interested in what aspects are influencing the burning velocity. So we made a big database, including the wave conditions, currents, type of fenders, type of marine structures, occupancy of the bird, if tugs were used or not, type of thrusters, if the thrusters were used. So to check what are the variables that influence the burning velocity. And typically in Rotterdam, you see this type of approach, that the vessel is stopped like 30 or 20 meters in front of the fenders, and then it's gently pushed towards the marine structure. So a very controlled parallel landing procedure. You see the data collected in Rotterdam during the 3 months within the stormy season. So you can see that the correlation is a little bit lower compared to vessel size, compared to the PIANC guidelines. Conditions in Rotterdam are quite sheltered. The mean velocities were about 3 to 4 centimeters per second, and the maximum velocity measured was about 10 centimeters per second. We also measured quite low burning angles. So this is only 3 months of data. So the Ever Given, for instance, the big container vessels are in this range, and then we have the post-Panama, New Panama, and the small feeders and coasters are in this area. So the small container vessels, and here you have the big container vessels. So this picture completely changes when we take a look at the data set of Bremerhaven. So same vessels from Rotterdam sometimes sail to Bremerhaven. You can see much bigger velocities compared to the velocities that were measured in Rotterdam. So we were asking, why is this the case? What's happening? What's the difference between Rotterdam and Bremerhaven? At first, Bremerhaven there's a strong tidal current, and the berthings, they are more or less an angular berthing. So the approach angle during the berth is much, much bigger. Also, the mean velocity was about 50% higher. And there seems to be a kind of limiting value in this data set of about 20 centimeters per second. We use this data set within 145. And then we did all kind of statistical analysis, and we predicted already higher values than 20 centimeters per second. And because the Port of Bremerhaven is still measuring the velocities, they provided us with a new data set in 2018. And this data set already included a higher velocity of 26 centimeters per second. I will show it in a moment. But it's also worth mentioning that the burning angle at the moment of impact in Bremerhaven was generally always between 0 and 1 degree. I will come back to that later on. So they have now we used about 8 years of data, and I think right now they have about 11 years of data of the burning velocity in Bremerhaven. So a very big data set. Also, Joko Brolsma, who developed the guidelines in the existing PIANC guideline, he did also some extreme value theory. So we are not looking for the mean burning velocity, we're looking for extreme burning velocities which might occur during the service life. So we did a similar analysis, also used extreme value theory in the PIANC committee, and two types of data sets were developed. In the guidelines called type B and type A data, which basically represent moderate and unfavorable navigation conditions. And these curves have a kind of probability of exceedance. So these are extreme velocities. And you see the data set below the curves. We had a big discussion going on. Is the data analysis, is it okay? Because first, during 2014, we didn't measure these extreme velocities, but in the bigger data set of Bremerhaven, you can actually see that one of the biggest container vessels in the world, one of the Maersk E-class container vessels, actually burdened with 26 centimeters per second, so much higher than the values that are presently in use. But this gives us much more confidence about the data analysis that was performed and that these values do occur in practice. So we found a bit higher velocities compared to the velocities that are currently in the guideline, especially for the larger seagoing vessels. And this will introduce a lot of discussion maybe, so I'll come back to that later. But first summarize the main findings of our working group. So we didn't find this strong relation between vessel size and burning velocity as was proposed in the previous working group. And we didn't find any evidence that burning velocity is directly influenced by the type of marine structure, type of fender, underkeel clearance. We didn't saw a relation with the number of tugs. No direct relation with environmental factors such as wind loads acting on the vessel, currents. And the main reason why we didn't found these correlations because they changed the burning policy. So the pilots, for instance, order an extra tug when conditions get worse, and maybe sailing through the port channels is more critical than the final landing procedure. And then they have probably additional capacity left, so they are more in control. So during stormy conditions, we sometimes saw lower velocities compared to normal daily conditions. That's because the pilots and the captains, they are more aware of the extreme conditions, for instance. They take that into account in the burning policy. So from PIANC MarCom, they said, they were asking, well, these high velocities, is there a trend break or do we need to double the fender size? Yeah, we add a disclaimer to the working group 145 report, say, please, just be careful using the higher velocities in combination with the existing PIANC guideline, because we also have a lot of new insight that need to be included in the new PIANC working group we are working on right now, the working group 211. And yeah, I will discuss some new insights with you today, and we can discuss it further within the breakout sessions. So at first, we recommend to use local or site-specific information rather than these general curves in the PIANC guideline. And if you have a burning aid system or a shore-based docking system, maybe there are burning speed limits which you can take into account in the design. Or if you have a big data set like Rotterdam, Bremerhaven, and other ports in Japan, then you can use this data to determine your own burning velocity. But there are, of course, a lot of situations where you don't have data available or local information. Then we recommend in the PIANC guideline, it's just a conceptual table, we recommend to use these values. So in contrast to PIANC Working Group 145, we added an additional column with recommendations for burning velocity for very favorable navigation conditions And these recommendations are based on the type A and type B birds that were presented before. But then we still end up with these high velocities for the larger seagoing vessels. And this might lead to bigger fenders. But there are some things that we need to take into account before we conclude that. We also looked into the reliability of the fender system by performing a full probabilistic assessment within the Delft University to check what are the variables that influence the reliability of the fenders. I don't think I have time to discuss it in detail, but I will highlight some of the things that we found. Of course, we have, when you are designing a berth, this can be facilitate small and large vessels or empty or fully laden vessels. So there could be a variation in the displacement tonnage of the vessel, which can be taken into account in the reliability analysis. Another thing we found is that recommendations for berthing frequency are lacking in the existing guideline. So some berths, there's only 1 or 2 vessels per year, whereas, for instance, public ferry terminals in Australia, then we have 25,000 vessels per year. That's completely different compared to what Brolsma assumed in the velocity curves in the existing guideline. So you can change the berthing frequency if you want, and this can really influence the safety factors we need to include in the guideline. And also, if pilots are on board, then we have the probability that a high velocity will occur is much lower. So pilots generally have a positive impact on fender design. Another thing is that if there's a strong relation between berthing velocity and fender size, so big vessels have a low velocity, for instance, this can also significantly influence the safety factors we need. Another thing which basically also new is the effect of multiple fender contact. So the values you see in this table are for different safety classes, but we recommend lower factors of safety if multiple fenders contribute in absorbing the energy. So generally we design for single fender contact at the moment. So one fender absorbs all the energy, and then the berthing angle is not so relevant. So all the uncertainty within the design of the fenders is related to the uncertainty in the berthing velocity. But as soon as you change the fender pitch a bit, so you add more fenders or bigger vessels are there, then the uncertainty in the berthing angle will play a major role also. So then the probability that a high velocity occur at the same time with a high berthing angle is less likely to occur. So we can take into account this effect. So you can see in here, if you change the berthing angle a bit, if the berthing angle is 0 degree, basically all the fenders are compressed at the parallel body length of the vessel, so they all contribute. For low berthing angles, much more fenders contribute in absorbing the berthing energy. And that's exactly why we don't see damage at the moment in Bremerhaven. So the velocity is much higher than the velocity that was taken into account in design. But the berthing velocity, the berthing angle that was measured was way lower. I think they made a design with 5 degrees, but in generally, we have 2,000 berthing records, and most of the records are far below 1 degree. And that's something we don't take into account. Higher values than 2 degree are not likely to occur, because then you will cause damage to the cranes which are installed on the quay walls for the container terminals, for instance. And also the data set in Rotterdam shows a similar image, and the same was in Japan, that berthing angles are much lower than what we take into account in the design. However, we still have a lack of data on berthing angles. And of course, there's also uncertainty in the shape of the vessel, the bow radius of the vessel, which can largely influence the outcome of the analysis. There are some other things we are working on within the committee, like vessel characteristics, the mooring loads. We have still an ongoing discussion about the allowable hull loading, the hull pressure criterion, new insights in panel design. Of course, we are going to provide more uniform recommendation for fender testing, which can influence the durability, and sustainability and recycling will be included in the new guideline. I think we have more time in the breakout sessions to discuss about these topics, but just to have an idea about the progress of the working group. Finally, I think it's good to mention, to share some of my experience within participating in working groups. My first working group started in 2010. Also, as a young professional, you have the opportunity to collaborate with all the experts in the industry. So that was a very nice experience. So I would encourage all young professionals to participate as well. I use the knowledge gap. So we have a lot of great discussions within the committees. I use it to determine knowledge gaps, and we can use that as input for new research. Of course, you have meetings in different countries, so you have the opportunity to travel a bit. And we also have a lot of online meetings. That works fine, but maybe the process will be a bit longer if you have a lot of online meetings and you don't know each other. We can present the next update. There will be a big technical session in the PIANC conference together organized by COPRI in Ports 22. So I hope to see you all in Hawaii. Thank you very much for your attention on behalf of Working Group 211. We hope to see you all in the next conference, and maybe we can discuss further in the breakout session. So please let me know if you have questions about the progress or things which need to be included in the guideline. We are happy to discuss. Thank you.
Thanks very much, Alfred, for a great presentation. I was wondering if we can have just a quick question at this point, is that we are having an inquiry regarding your berthing velocity data and whether it has been included to have the icy conditions for during the analysis. Like, do we have data from ports? I realize that you've had a very sort of a diverse range of participation from around the globe, really, from different countries. But how about like the different climatic conditions? That's the question.
Yeah, we have mainly collected data in relatively well organized ports. So like data from third for developing countries are not yet included. So for instance, like in Africa, also we don't have data from Norway or Sweden or other parts in really icy conditions. There are people participating from Norway in the committee, so who are familiar with vendor design in that region, but we didn't collect data on burning velocity in icy conditions. No.
Ethan, thanks for pointing it out, because I think one of the themes in the report is that I think one of the discoveries is that the actual operational policy is very important regarding the bursting velocity, and it's interesting to know around the globe how that changes. That's something that I think it's something that's very. Of course, I realize having a compendium which is like 200 pages or more, and trying to do that in 15 minutes is a real hard challenge. So I thank you very much, and I'd like to at this stage introduce our next speaker, who is Professor Evert Latter. He's the head of the Maritime Technology Division of the Ghent University, and I would like to invite him to start his presentation regarding the Ever Given incident at the Suez Canal, please.
Thank you, Babak, for your nice introduction, and hello everybody all around the world. I would like to have a look at mainly on the hydrodynamics happened at the Ever Given incident earlier this year. So it fits kind of into MarCom Working Group 121 on harbor approach channels and design guidelines. So as mentioned by Babak, I'm a head of the Maritime Technology Division of Ghent University in Belgium. Basically, we do everything that floats, so that goes from aquaculture, seaweed, mussels, in waves and current, and having a look at the forces involved there. Also floating PV panels, even the load-bearing glass on mega yachts. We create our own visualizations of the water surface as well for simulations. Later more about these simulations. And even on hydrofoils, we have an open source code on hydrofoils to find out the dynamic stability of these hydrofoils. But our real niche is slightly different than these topics, and that lies within ships maneuvering in shallow and confined water. We have a knowledge center for this, which was funded in 2008, but actually all expertise and all research on the topic goes back to the 80s of a previous century. So there are two partners in this specific knowledge center. That's on one side my research group at Ghent University, and on the other side it's Flanders Hydraulics Research, also located in Belgium. And it's within this knowledge center that there is the link to the Ever Given incident. And as also Alfred mentioned before, there is enormous increase in the size of the biggest container vessels in the world. So he mentioned that the rules of the fendering were originated from the 70s of last century. Well, at the time, the biggest vessel then could not carry more than 3,520 feet containers. So that means the biggest container ship in 1975 could carry 3,500 containers. And you will see an increase, but even in 1995, it was not even 5,000 containers, which fits on a single container ship. And then over the years, we saw a rather gentle increase up to 2005, when it barely reached 10,000 TEU. At the time, we thought that that's going to be it. It's a big vessel. All of a sudden, there was this vessel, which is the MarCom, almost out of the blue, all at once. There was a ship which could carry 14,000 containers, which was a kind of a shock. I said, no, it's going to be the biggest one for quite some time, but we were wrong again. So the number of containers that the biggest container ship could carry kept on increasing. And as we speak today, we are at 25,000 TEU. And I don't dare to say that it's going to stop. Maybe it will, maybe it won't. But there is one specific thing on all these ships. Actually, since the MarCom vessel, so this vessel, all of them didn't increase in ship length. So all these container ships are about 400 meters long. In order to fit more containers on a single ship, the ships got wider. So basically they added rows of containers up to 24 more or less nowadays. And by splitting the bridge from the engine room, then you could carry more or higher containers, and you could carry more containers behind your bridge. So the ships basically, they didn't get longer over the last decade. They got wider. The bridge moved forward in being able to carry more containers higher on deck, so a higher windage area. In the case for the Ever Given, it could carry, or it can carry about 20,000 TEU. So we are somewhere here. So it's a big container ship, one of the bigger ones, 59 meters wide. But all these ships, as well as the MarCom, they have a draft of about 15, 16 meters as well. So again, only wider, and containers got stacked higher. Now, if we move with these ships to shallow water, something happens to the hydrodynamics. What we compare here is 3 times the same turning circle. So in the first case, we express the water depth. So here, the water depth to the draft ratio. This is known as the under-keel clearance. So what is left under your ship? In this specific case, the draft is what you have between the bottom, the keel of your ship, and the seabed. So that's 100% UKC. And if we then sail with our ship at a constant forward speed, and at that speed we have a full rudder to port, for example, 35 degrees to port, then our ship will make a turn. This turn will have a diameter. But if we then move with the same ship to more shallow water, so for example at 20% UKC, so the gap under the ship gets more narrow, and we do exactly the same. So at the same speed, same rudder, everything the same propeller rate, and then we make a turn, and that turn will increase, significant increase. If we then move to even more shallow water as 10% UKC, and to give you an idea, this happens in reality. In Belgium, Netherlands, we have a canal where they sail at 8% UKC. And if we then look at the same effect, so we do the same, forward speed, full rudder angle, and we make a turn, then we see that the diameter of this turning circle increases dramatically. It's 3 to 4 times more compared to the deep water case. That's quite important, as compare this to a sports car to a truck. So basically you are in a device which is called a car, but you don't know whether it feels and reacts as a sports car or as a truck, and in between. So if we sail on a natural river, sometimes we are at 100% UKC, and at other locations much more shallow water. So the maneuvering behavior of a ship changes rather dramatically in these cases. And in order to investigate these specific maneuvering behavior, we have different facilities. So in Antwerp, Flanders Hydraulics Research has a rather modest-sized towing tank, 80 meters long, 7 meters wide, which has a fully automated and unmanned carriage. So we drag 4-meter ship models through the water in all kinds of conditions to find out this specific shallow water behavior of the vessel. That's Antwerp, and we also have a new facility in Ostend, also owned by Flanders Hydraulics Research, with also shallow water towing tank, but in this case 175 meters long, 20 meters wide. Today we can do free running tests, so fully automated free running tests, and the carriage will be installed later this year, and then next year we will be able to do again these captive model tests. So with, in this case, bigger ship models, 8 meter, we can drag them through the water and then look at the hydrodynamics involved. And then if we move to Egypt, to the Suez Canal, then we see the following. So this is not the situation of the Ever Given. This is a common situation where we have here the Suez Gulf, and then the Suez Canal towards the Mediterranean Sea. You can see it's located rather north-south oriented, and at this location it's a one-way traffic. So or there is a convoy sailing southbound, as it's the case in this example, or ships were sailing northbound, as in the case of the Ever Given. But what you see as well is that the width of the canal is rather restricted, and so that means that we don't only have that horizontal restriction on the Suez Canal, although the Suez Canal is relatively deep. We also have a horizontal restriction. And in order to investigate this specific phenomenon known as bank effects, over the past years, we have done enormous amounts of model tests in Antwerp. So different rectangular cross sections were tested, different slopes of banks, vertical keywalls, as in this example, a 1-to-1 scale, as in the Gaillard cut, for example, on the Panama Canal. Then we have slopes of 1-to-3, 1-7, and so on and so forth. A full range of geometries has been tested. A range of ship types and ship models were tested as well under these different banks. We varied the water depth, and as you can see, more than 1,000 tests, it's a logarithmic scale, more than 1,000 tests were carried out at 35% UKC or 100% UKC. So we get a database which is rather enormous. We varied the distance to the bank as well. And if we combine all this, we have more than 10,000 different model tests carried out only to find out what this specific bank effects, hydrodynamic effect of bank effects means and what it does to your ship. The real reason we do this is not for the research itself, but we want to create a mathematical model, which is then implemented into the simulators, and then we can use these simulators both for research purposes and training. But now let's have a look at a video, which is more than 10 years old, actually, of one of these tests. So this is the video we're going to see. So this is the bottom of our towing tank, so which is this part. Then we installed a sloped bank, which is then this thing. And then the yellow red line here indicates the air-water interface. So again, here, this is the dry part, so to speak, of the bank. And then here, there's a free surface. These balls are just spheres put there. So they are not connected or whatsoever to anything. They just float. And here we can see the ship model passing by. And what's quite important in this specific situation is that this water sails at a decent speed and it displaces water, but the water cannot go away. So it's squeezed between the bank and the ship. Because of that, there is Bernoulli effect, meaning there is a pressure drop. So water level drops. As you can see here, that this part, which used to be there, the free surface, is only there. So there's an enormous decrease of water level, and then there's a wave passing by. Now, if this doesn't seem to be realistic, a few years ago, we got this video in Flushing, the Netherlands, of I don't want to disclose the direction company who sails there, but we see exactly the same effect. So this wet sand is basically because of the depression between that ship and the bank, and then we see this wave passing by. Nobody got really injured, by the way, in this video. A few people got really wet. So we see the same effect. This wave comes by at exactly the same speed as the ship. So again, it's the water between the ship and the bank which is really squeezed and accelerated. So again, from the top view, we have a return flow on both sides. So that means the water flows in the opposite direction as the ship sails to. And this return flow, because of the restriction between the ship and the bank, is higher, as in the water flows faster, and that higher speed results in a lower pressure. So the ship as a whole gets attracted towards the seabed or the bottom, known as squat or running sinkage. And then typically, but not always, the ship is attracted towards the closest bank. That's why this effect is sometimes called bank suction. As we will see later on, sometimes it's a repulsion force as well. So we can decompose this specific force here into a longitudinal and a lateral direction. So this value x is basically an increase in resistance, while this is an attraction force. If we move it now to the center of gravity, then we need to introduce a bow away moment. So that means this ship gets slowed down, an increase in resistance. It gets attracted towards the closest bank, and her bow is being pushed away by this closest bank. So if we then have a look at this split, which is all the same, all the black arrows combine to exactly the same thing, as in an attraction force to the aft and then a force at the fore, then we see the following. So if we focus first on the attraction force at the aft, then the rather obvious thing, the closer we sail to the bank, the higher the magnitude of this attraction force. The faster we sail, the higher the magnitude of this attraction force. At the fore, it's slightly different. At the fore, we saw that it depends on the water depth. So if we sail at a certain position in deep water, it's an attraction force. In magnitudes, by the way, lower than the attraction force at the aft. So that results in a bow away moment as well. But if we sail in very shallow water, then there is a pressure region between the ship and the bank, resulting in a high repulsion force. So in this situation, the ship gets even pushed away from the closest bank. Now, if we sum up the effect on the ship is as follows. So if we sail close to a bank at decent speed, then the ship might be attracted. In deep water cases, it's going to be attracted towards the closest bank. It might be repulsion in more shallow water, but in all cases, it's a bow away moment. So this arrow is always the same. It's always with the bow getting away from the closest bank, no matter whether it's deep or shallow water. This attraction force or this sway force can be compensated by drift angle. The yaw moment needs to be compensated by rudder action. That's a rather important nuance. Now, back to the Ever Given. So in March of last year, the Ever Given crashed into the eastern bank of the Suez Canal. So if we take a cross section, then you can clearly see, this is of course simplified. I don't get any confidential information. All information I got from publicly available AIS data. And then if we have a look at the specific cross section on the canal, then we see this is the canal on full depth, about 25 meters, and then there is a slope bank on both sides. So that means that the full depth is restricted. It's less than the width on the free surface, and then we see there's enormous amount of or how deep this bow basically plugged into the eastern bank, and then there was a rotation sliding the stern on the western bank. But there's something quite specific I would like to show you on the AIS data. So first of all, the Ever Given was sailing northbound. So it's a northbound convoy. So these yellow arrows are all big as in more than 10,000 TEU, big container ships sailing to the north towards the Mediterranean Sea. And at the back, you can see there's a blue arrow behind the first two vessels, and in this one is the Ever Given. It did not have such a blue arrow. That blue arrow is a tugboat. It might be a bit odd or strange to have a tugboat at your stern here, but this is how this works. So the faster you sail in shallow or confined water, or any water, basically, the higher these hydrodynamic effects are going to be. If you sail fast, then the bank effects, the squat effects, and any other effect will be higher. So the forces on your ship will be higher. But if you sail slow and you don't, or you have a very low propeller rate, then there is not a lot of water flowing around your rudder. So that decreases your maneuverability. So actually what you want to sail slow in order to minimize hydrodynamic effects in these situations, but you want to have a lot of water around your rudder, so at a high propeller rate. And in order to avoid that your ship accelerates, you add a tugboat. This tugboat slows down your ship. So then you have the combination of a lot of water around your rudder. So your rudder is going to work very well in combination with modest hydrodynamic effects. Such a tugboat was not available on the Ever Given. A second thing, which is quite not striking, but a conclusion you can draw, is that this ship sails here at more than 12 knots. That's rather fast, not super extreme, but there are different reasons why this ship sails so fast. First of all, there was a northbound current. So this speed here, AIS speed, is speed over ground. So the water in the Suez Canal streams towards the north. So that adds up a velocity which you cannot counteract. You simply float with the current. On top of that, there was also a southern wind, so a decent wind, a strong wind, pushing this enormously big ship, all these ships, also towards the north. So that adds up as well. And the effect with wind is basically the faster you sail, relatively, the lower the wind effects are on your ship. So actually you want to sail fast in order to minimize and have better control of your wind effects. But here we see the Ever Given on the canal. You can see it also a bit moving from left to right. So you can see it's not sailing on the central line of the canal. It's slightly towards the east, at least as far as this AIS data is reliable. It seems to be. So in this situation, sailing close to the eastern bank, there might be an attraction force, there might be a repulsion force due to the bank effects, but there will be for sure a bow away moment. That means that the bow of the Ever Given in this location is pushed towards the west. At the end, we have a propeller rate pushing our ship forward. So that combination brings your ship more to the west. As we see here, at this point, actually a little bit before this moment, to me, there is no discussion what's going on. At this location, the ship is still sailing more than 12 knots. It's sailing very close to the western bank. Again, bear in mind, it's a trapezoidal cross-section, so that means that the free water surface is much wider than that narrow deep water. Okay, so the ship is very close to the western bank, having a propeller rate, so being pushed forward by its own propeller, and having an enormous bow away moment. That combination results in a bow away moment which is so big that it is impossible to be compensated by the rudder effects. At this speed, sailing so close to a bank cannot be compensated by anything. There is not a single rudder in the world which can compensate the bow away moment which is induced at this point on the Ever Given. So what happens next is the ship gets an enormous rate of turn. It starts to turn because of that bow away moment, being pushed forward by its own propeller, and then it crashes into the eastern bank. And that's what happens there. So, from that point, it can be kind of be lucky that the next vessels in the convoy were able to stop on time, because the stopping distance also decreases in shallow water. But at this point, the ship was already really deep into the eastern bank. Here we have some tugboats who try to get some motion into the ship, but as all of us know, it took 6 days before the ship was freed. Now, again, we did our model test, we made a mathematical model, and then we have the simulator. We can use the simulator, you can buy a simulator, but because of all the research we've done on the topic, we are capable of having a look at the forces and moment involved. And for us, the simulator is a device for research, not for training. So we can switch things on and off. And actually, this track, it's a part of the Suez Canal in which we've we've done or mocked the simulation twice. Once we've switched off the bank effects, which is easy to do on a simulator, not in real life, of course. So now we see that the autopilot could easily keep track, so sail quite close to a bank, which doesn't introduce any hydrodynamic effects on the ship. The yellow curve is actually with the bank effects on, and then we see this wobbling effect of a ship, which is quite common with bank effects, as in you just compensate one bank, but because of that, you end up too close to the next one, and this effect increases bank after bank, and then until the moment that you crash into the other bank than the one which introduced the real problem. And that's again what at least is the final position of the Ever Given, why it crashed into the bank. I cannot say, because I simply do not know, why they ended up so close to the western bank before the crash. So it might be, and it seems also a bit because of previous bank effects. Could also be very other and different reasons than that. For that, I like the necessary information on the incident. Which brings me to the end of this presentation. I have no idea if there is time now for questions. If not, then ask your questions in the breakout room later on.
Thanks very much, Egbert. That was very informative presentation, and also elucidating how the bank effects have been contributing to that incident. I think that since we are running a little bit behind the schedule, we keep the questions for the Q&A session. I'd like to invite our esteemed panelists to join me so that we can try to cover as much questions as we can. And if not, then there's been envisaged to have a sort of a brainstorming session in different breakout rooms, and I invite everyone to contribute to that in case that the questions won't be able to get all answered during the continuation of the webinar. So firstly, I'd like to thank at this point also Mr. Ed Backlund for all the wonderful effort he's done in organizing this webinar, and also like the fantastic job he's been doing as the YPCom observer within MarCom. Now I'd like to invite everyone to start the Q&A session, please. So again, at the beginning, I'd like to personally appreciate your presence and for the 3 illuminating presentations that we've had. It's been really enjoyable and a privilege to hear them. And since we got a lot of questions, and I tried to, with apologies, I tried to sort of combine some of them at times. So I think we start, if Ashabi, we could have your response, please. We have 3 questions which are essentially concerning the sustainability case. The sustainability case for the container automation of container terminals. You've made the business case for it. For it to be holistic, we need to have also the sustainability angle weaved into it. So now, please, if you could briefly, like, just point it out to us how you have gone about that.
So when we say automation, usually it goes hand to hand with electrification. So by electrifying the systems, we are reducing the emission that is generated by this container handling. Secondly, even by making the system efficient, the time that it takes or the effort that it takes to move a container will be significantly reduced because we are making it efficient, less handling. It is a well-thought plan. So that itself reduces the emission. In some of the studies that we've done in the past, it comes close to 98, the only 90 to 98% reduction. And the reason of that percentage that is not removed is still we have to receive and deliver these containers from outside tracks. So even that, if we manage it efficiently, we can significantly reduce the queuing of tracks. One of the most important part of automation is the separation of the water side and land side traffic. So you can manage both very efficiently, and you don't see trucks queuing and emitting into the air, both which is bad for the local and bad for the whole overall environment.
Thanks very much. I really appreciate that you answered from an environmental perspective, but then how about the social perspective? Because we do have a question from one of our participants from a developing country. They are concerned about the potential loss of employment that could result from automation.
Yeah, and again, it is a shift. Some of it is shift from unsafe, tedious, repetitive job into safe job. But this is not only in container terminals. It's in all industrial systems. This is the way we are moving into getting things done by missions that are unsafe, if it's done in person, unsafe, and then reducing the impact on humans, the repetitive physical jobs. However, when you do that in any industry, there is a reduction of labor demand. But we don't do things to just employ people. We do things to help employ people in something productive. So that question is not a terminal operator's question. It is the whole country's and global issue that needs to be resolved. How do we transition?
Thanks again. And I'd like to ask Alfred if he can please take on this question. We have some interest for regarding like bursting velocities regarding smaller vessels, especially fishing vessels, since they cause a lot of accident and damage, but there is not usually as much data available. And how have these been incorporated in the report?
Yeah, there's still a discussion going on, but within PIANC 145, small vessels were not taken into account. Only vessels with a deadweight tonnage larger than 30,000 were analyzed. With the mobile laser in Rotterdam, we were not able to shoot at the parallel body length of the vessel. So because the parallel body length is generally below the top side of the quay wall, so that was not possible. I think we still need to collect globally more data about the smaller vessels, the inland barges, the small seagoing vessels. We still have a lack of data on these type of vessels, so they are not included. We still have a lack of or knowledge gap there.
Thanks. And also on a different note, your results seem to point that the previous dependency that was supposed to be a negative correlation between the vessel capacity, the deadweight tonnage, and also the berthing velocity it's been seen to be less valid. And now this may lead to potentially an increased cost for vendoring for future projects. And then if this has been incorporated into the guidelines, and do we have to really think about that since we don't have that much damage at the present time? Now, this is something that are your results going to point to a full revision of Working Group Report 33, or are they going to be more in line? That's like, how do you respond to that, please?
Yeah, so the objective of Working Group 211 is to replace the Working Group 33 report completely. And then, we have to deal with the higher velocities because they have been measured, so we cannot neglect it. So we need to somehow take that into account. But at the same moment, we didn't observe damage of the fenders in Bremerhaven, for instance, and other ports. So there must be a reason for it, but it's not the high velocity. So there are other things which might be conservative, or we have maybe the targets or the safety factors we apply might be higher. But we couldn't guarantee that some data sets, they didn't show any correlation between vessel size and burning velocity. It was simply not there. Where the data set in Rotterdam, this shows a very gentle relation. And also one bird in Japan showed this relation. But most of the data sets, if you look at a specific data set, then you don't see a relation at all. So we cannot guarantee that. Only if you have measurement, you can prove that there is this correlation, but it's not. It was not observed everywhere.
Thanks very much. Now I think that for questions for Evert, sorry, I have to look at the other screen for a second. Now we have received a number of questions. Evert, could you please respond to this question? Is there a speed limit for Suez Transit in this particular area for VLCVs, CVCs? And sorry, VLCVs, and what is the normal speed for that? And also there's another question: what was ever given speed at the time of the incident? So this is like maybe I should repeat it once more. Is there a speed limit for the Suez Transit at this particular area for the very large container vessels? And what's the normal speed that's expected there? And what was the ever given the speed at the time of the incident? Sorry, there's a couple of questions all together.
I didn't check the nuance of the speed limit on the Suez Canal, so I cannot answer on that one. I thought there was the nuance. I mean, is sometimes that imposes kind of a restricted speed limit, a very fixed one, and sometimes it's more nuanced as a recommended speed limit. The important thing here is that it's not always simply possible or a good thing to reach that speed limit. The ship seems to sail fast. That's out of the question. But as mentioned before, it's speed through the water, which is of importance. So if the current goes north, if the wind pushes, then you need to achieve a certain speed. So that's not too of important. But before the crash, the ship was sailing more than 12 knots. And that's enormous. So 12 knots, so close to a bank, that's an enormous... that's very fast, so close to the bank. Whatever speed limit there is, or there is not. But again, we see it on other channels as well. Is that speed limits are imposed, but cannot be achieved because of these environmental conditions and circumstances, basically, which overrule and that speed limit.
Thanks a lot. And I would like to return to Ashabi
Can I add
again.
one more thing?
Please.
And this comes in combination with the convoy. You need to stick to the convoy. So basically, all ships have the same speed. That's also a tricky one, because have you seen, quite after the crash, the next ship was already quite fast to you. So the entire convoy tries to manage more or less to have the same speed. That adds up to the you get pushed towards a certain speed, maybe which you don't want as well.
Just like before we leave this topic, how quantitative the physical modeling results can be for a case like this?
In order to avoid to go too much into detail, but the effect is a Bernoulli effect. So that scales very well according to the fruit law, and we do our model test according to the fruit law. In other words, there is some nuance of viscosity, because that's the main problem in model tests. But on bank effects, unless you sail extremely close, and then I'm talking about much closer than the case of the ever given, then viscosity effects come into play, but that's not the case here. So that these Bernoulli effects, these fruit effects, inertia, gravity effects, they scale very well to this one. The viscosity effects do not. We try to tackle that one differently, but that's a kind of an easy scaling to full scale for these kind of effects.
Thanks very much. I think that we try to squeeze in one more question from each one of our esteemed panelists. Actually, could you please provide some response regarding the selection process when we are going to, basically we have different things interplaying when we are deciding to go for a semi-automated, a manual, or a fully automated container terminal. And there are questions in the audience how the issues of the capital cost, the maintenance cost, and the savings on the future operational costs interplay in this selection. I'm trying to combine a few questions here, and essentially it's concerning what are the cost benefits for such a decision and how they actually govern the essential final choice.
Yeah, thanks. That's a good question. The first part, it is the selection of fully automated or semi-automated. Usually two drivers to it. Some choose to go semi-automated because they don't want too much complication. They want, it is not really true, but that there is that belief. I'm fine with what I achieve by using man's horizontal transport, so I'm going to go with that. Secondly is that social impact, the labor, the horizontal transport, like in certain parts of US, mainly on the East Coast ports, the deal with the union is that the horizontal transport cannot be fully automated. So that can be another driver. But in terms of the financial modeling, we look at everything as an input. What is the OPEX benefit and what is the CapEx? So let's say if I'm choosing between a fully automation, my CapEx for the equipment may be higher. However, my OPEX is reduced. I need less people to operate them. Then the financial model will have to identify what the return of investment is. And that is why it is important to have a reliable financial model that goes during that process.
Thanks very much indeed. And at this point, unfortunately, we have run out of time, but I'd like to thank our esteemed panelists for providing very interesting discussions on 3 different topics. And I think that we have this plan to actually continue the brainstorming and the remaining questions that we didn't get to answer during the breakout sessions that are going to follow. And there has been one room allocated to each one of our panelists, and you can please feel free to ask your questions. And there are also other rooms available if you have general questions about MarCom and also about PIANC in general. And I think that it's a very hard task to try to say anything at this point, but I think that what we could conclude at this point is that looking at 3 different interesting topics, very diverse, and all very much in line with what are the latest developments and the needs regarding the industry and how it's developing. I think that we could just say that at this point that MarCom is also sailing ahead, and also it's very much inviting your feedback and your reflections about how to proceed, and that can be actually very part of these conclusions. So I'd like to invite you to basically continue the discussions during the breakout sessions, please. Now, for going to the rooms, there is a very simple procedure, to start the breakout. You have to just do 2 clicks, one on the red rectangle and then on the yellow one, and then you can choose your own room that suits your interest, and feel free to have a direct interaction with our panelists, and then we can actually continue from that point. It's been really a true honor to be with you, and I also will join you later on in one of the rooms. Thank you so much.